D is definitely the trickiest one in this set. They say boron has a lower first ionization energy than beryllium. So let's go through our kind of arguments here. Let's see if it's effective nuclear charge. If it's effective nuclear charge, well, here's boron and here's beryllium. You notice that boron, having more protons, will have more effective nuclear charge. It'll be pulled in, all the electrons will be pulled in closer. And I think they will be more difficult to remove on boron. But you notice they say boron has a lower first ionization energy, which implies that they're easier to remove. So I don't think effective nuclear charge is going to be an argument. We might rule out shielding as well, since they both have one core electron. And then we could go to electron-electron repulsions. And that might seem to be the argument to make here. Boron has more valence electrons. It has 1, 2, 3. And so having more valence electrons, they will repel each other, it will be out further, and therefore boron will have a lower first ionization energy. However, that's not the argument I'm going to make here, and I'm going to show you the argument I'm going to make in a minute. So this over here on this side is the electron configuration of beryllium. It has 4 electrons, 2 in the 1s, 2 in the 2s. And you notice in the 2s, as we kind of were predicting, there's 2 electrons in the first shell that can shield the electrons in the beryllium. But boron has 1 more electron, it has 5, so it has 1 more in the 2p. You notice we always draw the 2p's just slightly higher in energy than the 2s, which means that the 2s's can sort of shield those 2p's. And so we're talking about shielding based on sublevels here, which is really rare in AP, but they seem to have asked it here. So the 2p electron actually has 4 electrons that are shielding it. So I'm going to make a shielding argument. Alright, so boron has lower first ionization energy than beryllium because boron's 2p valence electrons has 4 core electrons shielding it. Beryllium's 2s valence electrons have 2 core electrons shielding them. So that's the argument that we made over here, thinking through our orbital diagram. Therefore, the greater shielding of boron's valence electrons will result in less Coulombic attractions and will require less energy to remove. So I think that's a pretty good argument, and I think it's the one they're looking for. You know, if you're still wondering, would the electron-electron repulsion argument work better here, or would they at least take it? Because remember, we were saying that boron has more valence electrons. You could say that it has 3 valence electrons, whereas beryllium only has 2. And I'm not sure if they would take it or not. The key from this year did not imply that they would take it, but some people might say that that's a reasonable argument as well.